So we begin the last chapter in this course. So we are going to study compact operators. So compact operators are a special class of continuous linear operators which mimic a lot of properties of finite dimensional operators. So we start with the definition. Let V and W be Banach spaces. Let T belong to LVW. If dimension of the range of T is finite, we say that T is of finite rank. If the image of every bounded set in V is relatively compact, in W we say that T is compact. So remark, so we need to check, so T is compact means if BV is the closed unit ball in V, then T of BV, this need not be closed, we have seen examples, closure is compact. Alternatively, given any bounded sequence Xn in V, there exists a subsequence Xnk such that T of Xnk is convergent. Because Xn is in a bounded set, its image is relatively compact, and in a metric space compact means sequentially compact, and therefore you have a convergent subsequence. Okay, so examples. So a ball, a bounded set in a finite dimensional space is relatively compact. Therefore, hence, any operator of finite rank, because the image will go into a finite dimensional space and it's bounded, so it will be relatively compact, is compact. So if V is finite dimensional, then T from V to W is always compact, because it is of finite rank and therefore it's always compact. Okay, so example again. V infinite dimensional and I from V to V is not compact, because BV is not compact, and that's the image of the unit ball, and therefore BV is not compact, and therefore if you have the identity map, then it is not compact. Then example again, if T and S, so T belongs to L of VW and S belongs to L of WZ. So VWZ Banach. If any one of these is compact, then S composed with T is compact. Because continuous linear maps take bounded sets to bounded sets and compact sets to compact sets. So when you have any bounded set, then the composition will always be a relatively compact set. So if T is compact, then T is not invertible. Because if it were invertible, then T composed with T inverse or T inverse composed with T is the identity map. So if one of them is compact, then the identity must be compact, which is not true in an infinite dimensional space. Okay. So up to now we've been sort of not giving very serious examples, except the identity is not compact. That depends on the deep theorem. So now let us give you a real nice example. So consider the inclusion map I from C1 01 into C01. So let me put I hat so that not to confuse with the imaginary I. Okay, so this is the inclusion map. Okay, now C1 has its norm, namely maximum of norm f infinity and norm f dash infinity. Okay, so that's the norm in C1, and here is the usual sup norm f infinity. So with this usual norms, then with the usual norms which make them Banach spaces. Okay, so with these usual norms, then we want to show that this map is compact. So let us take so norm f 1 infinity is max of norm f infinity and norm f dash infinity, and therefore if norm f n 1 infinity is less than or equal to C, this means that norm f infinity is also less than or equal to C. Okay, so this sequence is bounded. Now we also have that norm f dash infinity is less than or equal to C by the mean value theorem. So you have mod fnx. You don't need a sequence here, let me say. Okay, so mod fx minus fy is less than or equal to norm f dash infinity times mod x minus y, and therefore that's less than to C times mod x minus y. Okay, therefore set of all f says that norm f 1 infinity is less than or equal to C, is uniformly bounded and equicontinuous, and therefore by Ascoli's theorem, okay, that the image is relatively compact because 0 1 is a compact set, and therefore implies I hat is compact. So this is just a direct consequence of the Ascoli theorem. Example again. Let K belong to C of 0 1 cross 0 1. Okay, and let small k equal to sup of k of xy xy belonging to 0 1 cross 0 1. Okay. So now for f in C01, define Tf of x equals integral 0 to 1 of k of xy fy dy. It's all continuous functions on a finite interval, so they are all integrable, and you have mod Tf of x is less than or equal to k times norm infinity. Therefore, norm Tf infinity is less than or equal to k times norm f infinity, and therefore T is a continuous linear transformation of C01, and this is also continuous. Tf is also continuous, that again you can check, and therefore in fact we will see it in a moment. So this is a continuous, so T maps C01 into C01. You have to check that this is a continuous map, but that's very easy to check. So if you, because of uniform continuity of k. Okay. So now if norm f infinity is less than or equal to c, then you have norm of Tf infinity is less than or equal to k times c, and therefore they are all uniformly bounded. Then what about mod Tfx minus Tfy? That's less than or equal to integral 0 to 1 mod kxt minus kyt ft mod ft dt, and that is less than or equal to c times sup mod kxt minus kyt x in C0 xt belongs to C0. Okay, so now k 0 1 cross 0 1 is compact, and therefore k is uniformly continuous. Therefore there exists, given any epsilon, there exists a delta such that mod x minus y less than delta implies k of xt minus k of yt is less than epsilon, and therefore mod Tfx minus Tf of y is less than or equal to c times mod x minus c times epsilon for all mod x minus y less than delta, and for all norm f infinity less than or equal to c, and therefore you have again uniformly bounded and equicontinuous implies T compact by Ascoli. Okay, so Ascoli's theorem again tells you that T is compact. Another example, let A from 0 1 to R be continuous and A is not identically 0. Okay, define A from L201 to L201 by AF of T is AT ft. You're just multiplying by continuous function. A continuous function on a compact set is bounded. So if you're multiplying by a bounded function and a L2 function, it's again an L2 function. So A takes L2 into L2. Okay, so and also you can check that A belongs to L of L201. All you have to do is norm AFT square is mod AT square FT square, which is less than the sup of A square times norm F square. Okay, so it's also a bounded linear operator. Okay, let A of T naught be not equal to 0. Okay, so T naught in 0 in the interval. Okay, then there exists J equals T naught minus alpha T naught plus alpha contained in 0, 1 such that mod AT is greater than or equal to 1/2 of mod AT naught, which is strictly bigger than 0 for all T in J. It's just a continuity condition. It's non-zero at T naught, so in a small interval it will also be non-zero, and we can choose the epsilon to be half of that absolute value, and therefore you will get this condition. Okay, so let Fn tilde be an orthonormal basis for L2 of J. It's also an interval, so you have it's a separable space, so you have an orthonormal basis. So you now define Fn of T is equal to Fn tilde T if T belongs to J, and 0 if T belongs to 0, 1 minus J. Okay. Then norm Fn T equal to 1 for all n, and if n is not equal to m, we have norm A of Fm minus Fn, A of Fm in L2 whole square is equal to integral 0 to 1 of mod AT square mod FNT minus FMT square dt, and that this integral will survive only over J, because outside J Fn and Fm are all 0, so this is greater than equal, and on J what you have about AT, it is 1/2 of AT naught square, so you have mod AT naught square over 4, then Fn minus Fm is integral over J Fn tilde T minus Fm tilde T square dt, but that we know is in fact 2. This is equal to 2, because if you have an orthonormal in a basis, then norm of Fn minus Fm is always 2, so that's equal to mod AT naught square by 2, which is strictly positive. So this means that A of Fn does not admit a Cauchy subsequence, and therefore this implies A is not compact. Okay, so now we have given a fairly good number of examples. So now let us prove the following. Study the properties of compact operators. So proposition, let V and W be Banach, let K VW be the collection of all compact linear operators from V to W. Then KVW is a closed subspace of LVW. So proof. So KVW is a subspace. Easy to check. If sum of two compact operators is again compact, scalar multiple is again compact, therefore this all is a subspace. So we have to check to show Tn in KVW, Tn converges to T in LVW implies T belongs to LVW. Okay, so that's all we have to show. So the limit of compact operators in the operator norm is in fact a compact operator. Okay, so let BV be the closed ball in B. Okay, so to show T of BV, so we are not, since we put a special, take any ball. So T of B is relatively compact. So all that we are in a metric space, and therefore it's enough to show that it is totally bounded. So given epsilon, then we can, that is, given epsilon, we can cover TB by a finite number of balls of radius epsilon in W. Okay, so this is what we want to show. Okay, so norm Tn minus T goes to 0. So given any epsilon positive, there exists an n such that norm Tn minus T is less than epsilon by 2. Now Tn is compact, is given. So Tn of B, it can be contained in union I in I, B of BW, Fi epsilon by 2, where Fi belongs to W and I is a finite set, finite indexing set. BW is the ball center Fi and radius epsilon by 2. Now norm Tn minus T is less than epsilon by 2, and therefore this implies that norm of the TB is therefore contained in union I in I, BW of Fi epsilon. That's immediate to check, and therefore this implies that T is compact. So corollary, let Tn belong to LVW be compact, be of finite rank. Let Tn converge to T in LVW. Then T is compact. Okay, so that means because any mapping of finite rank is compact, and now limit of compact operators is compact, that is what we have already seen. So the limit of operators of finite rank is always a compact operator. And an interesting question is the converse true? That is, can every compact operator be approximated by operators of finite rank? It's not always true, but we will see cases where it is true. There we'll also do some exercises in this connection, and we'll continue with this.